All right. So first off, quick warning before Tom gives the introduction. We are trying something new again with Tech Talks. This is being live streamed on the internet. Hi, internet. So, fair warning. Tom.
So we have with us Max Brunsfeld from GitHub to talk about his the parser library tree sitter. He just gave this talk at the GitHub Universe conference, and it was very enjoyable. I hope you enjoyed it too. Max, thank you for joining us.
Okay, thanks so much for having me. So like Tom said, I work at GitHub. I work mainly on the Atom text editor, which, if you're not familiar with Atom, it's a code editor we built at GitHub that we designed to be user-friendly, but also highly hackable, so every part of the application can be customized to behave however you want with using CSS and JavaScript. I'm here today to talk about this library tree sitter that I've been working on for about 4 years, first as a personal side project, and now as part of some production systems at GitHub. So I'm going to explain what tree sitter is, and then I'll talk about why I chose to write this new parsing library. And then I'll show you some of the things that we have done with tree sitter so far at GitHub. And then finally, I'll talk about some of the algorithms that tree sitter uses. And please feel free to interrupt me and ask questions or talk about something else at any point. I'm totally fine going way off of this outline, but we'll get started. So what is tree sitter? So tree sitter is a library for parsing source code. It's written in C and C++, and it's designed to be used in applications like Atom or GitHub.com that deal with code written in many different languages. And so the idea is that you can use tree sitter to parse files written in a variety of languages, and it'll produce syntax trees for you that all have the same API and the same format. But the really unique thing that tree sitter can do is what's called incremental parsing. And that means that once you've parsed a file with tree sitter and you have the syntax tree representing that file, you can then edit the file, and tree sitter can quickly update the syntax tree for you to reflect the change that you made without having to reparse the whole file from the beginning. And so this is the feature that makes it possible to use tree sitter in a text editor like Atom to do parsing in real time on every keystroke while the user is typing. So now I'll explain why I decided to write tree sitter. Overall, my goal is to make software development easier by making programming tools more powerful. And so for me, that means enabling them to understand source code better and analyze source code better. I get the impression that at Galois, you're believers in the value of automated source code analysis for things like proving the code has no bugs and finding bugs in code. And I think that's really cool. And I also think that source code analysis can be used in all kinds of simple ways in everyday programming tools to make them more useful to people. And so there's lots of great systems for doing source code analysis today already. And if you want to do a new kind of analysis, there's lots of great building blocks available to you for different languages. Like if you want to analyze C and C++ code, you can use libclang. Or if you want to analyze C# code, you can use Rosamund. And I'm sure the same kinds of things exist for many other specific languages. And yet, despite the existence of all these libraries, I would argue that many of the programs that we rely on the most today as software developers still only understand source code on a really crude level, if at all. So let me give you a simple example of this. One of the biggest things that helps us to read code is syntax highlighting. And syntax highlighting is something that we use pretty much all the time while we're working, whether we're looking at code on GitHub or on Stack Overflow or in our text editor like Atom or Vim or whatever. And you might not think of syntax highlighting as a form of source code analysis, but I include it in that category because, at least in principle, it requires that the program understand my code well enough to apply some kind of grouping to the different tokens in the code. And so let's look at an example of some typical syntax highlighting that we might see today on GitHub or Stack Overflow or Vim. So this is a piece of Go code that defines this person type and these two methods, getName, which returns a string, and getMom, which returns a person. And this thing about this example is that even though string and person are both types, they show up in different colors in this example, which is kind of a failure of the syntax highlighting system, I would argue, because the whole point of syntax highlighting is to color things the same when they have the same role in my code. So these two things both being types ought to be the same color. And this is a screenshot from Atom today, but you can see that the same thing happens in other popular text editors like Sublime Text and Visual Studio Code. And you'd see the same kind of thing all the time if you're looking at syntax highlighting, whether it's on GitHub or really anywhere that you read code. So as programmers, most of us are kind of just used to this situation, and we just think, yeah, of course, syntax highlighting is never all that accurate. It's not something that I rely on to help me understand my code, really. But thinking about the fact that there are all these great systems today for analyzing source code, why is it that applications like GitHub, and Stack Overflow, Atom can't do a better job at this really fundamental task of syntax highlighting, which we use all day? And so, if I had to break it down, to me it seems like there are a few main reasons why these existing parsing tools don't get used. And the first one that comes to my mind is performance. So in a text editor in particular, syntax highlighting is something that needs to update on every keystroke. And for the editor to feel responsive, it needs to happen in 1 or 2 milliseconds at the most. And so that right there kind of rules out the ability to use a lot of popular parsing tools, because most parsers that are built as part of a compiler toolchain are meant to kind of operate on an entire file. And for sufficiently large files, that's just always going to take longer than we have time for in this situation I'm talking about while you're typing. And then aside from performance, another big difference between these applications that I'm talking about and applications where we can use parsers that are built for compilers is that in order to compile a lot of languages, you need to know more than just the content of a source file. Or sorry, in order to parse the source file, you need to know other information besides what's in the file. For example, to use Clang to parse a C source file, you need to not only be able to read the source file you're trying to parse, but also all the other source files that it includes. And you also need to know other things like what macros are defined and other aspects of the build settings. And so that is just a different set of information than we have available to us in applications like GitHub or Atom, where we're just trying to syntax highlight some stranger's code that we know nothing about other than the code itself. And then finally, what I think is the biggest thing stopping us from using these kind of tools is the issue of dependencies. So for a lot of languages, the standard compiler and parsing toolchain for that language is written in that language and has its own dependencies associated with that language. And so in an application like GitHub or Atom, where we want to support a wide variety of programming languages out of the box, if we had to call out to a different external tool to parse every different source language, it would just add a ton of complexity to our app that we can't afford. And so the net result of all these things is that when you look at code on GitHub or in your text editor, these applications are just doing the best they can to syntax highlight your code by running simple regexes over the code, looking for simple patterns. And as users, we just get used to the fact that these types of programs aren't able to analyze code very well. The syntax highlighting isn't very reliable. And so that was kind of my starting point for TreeSitter. It's like, what if there were an accurate parsing library that these types of applications could use that was fast enough to run on every keystroke in a text editor and didn't require any extra information about a piece of code in order to parse it. It would kind of just do the best it could to parse a piece of code like a human would, seeing only that code, not knowing the build settings or whatever. And had no extra dependencies. In fact, it was a C library, so you could use it no matter what language your application was written in. So that's the goal of TreeStater. So you have a question?
I do.
Okay.
If you don't mind.
Yeah.
So did you just have this idea and then tell your team at GitHub, hey, I'm going to do this for the next year and a half?
I actually started working on TreeStater before I started working at GitHub. It was one of my foots in the door. Was like I had built an Atom package kind of a long time ago that hacked TreeStater in, so you could like this one feature that I'll show you later on. That was kind of the one feature that this package provided, and so I think that was kind of what how I got hired. So it's been an idea of mine before I even was an Atom user or a developer on Atom. So that's my motivation for developing it. Now I'll show you some of the things that we've built using TreeStater so far at GitHub. So since I've just been talking about syntax highlighting, I'll show you first our new syntax highlighting system. So here's a screenshot from Atom in which I've re-implemented syntax highlighting using the syntax tree provided by TreeStater in the editor. And so it's the same piece of Go code that I showed you earlier with the person type. Only now the problem that I mentioned earlier has been addressed. All of the types in the code now consistently show up in this blue-green color. And on top of that, all of the struct field names now consistently show up in this red color, whereas before they weren't differentiated from other names like local variables. Yeah?
So the previous way of syntax highlighting, you could easily say what syntax highlighting does. Maybe it does analyzes the lexical structure of the program. It tells you what each lexeme is, what type.
Yeah.
What is the definition of this? How do I know? So you told me, okay, types are common. How do I know what is the definition of syntax highlighting now?
Well, are you talking about how this is implemented or how?
Things are in different colors.
Yeah.
But what does that mean?
Well, the way that they're defined now is it's kind of a mapping of, you can select parts of the syntax tree with CSS selectors. So I can say things like if there's a member expression like self.name here, then the property name in the member expression should be colored with this CSS class. That's the way that this is defined. And so like conceptually, the way these are defined are like certain subtrees have certain colors, if that makes sense. And a lot of the subtrees are trivial, like type name is defined to have one color. And if I wanted, I could define local variables, like expressions that are evaluating a variable to be a certain color. But yeah, I don't know if that answers the question. It's like, yeah. Yeah, I mean, the problem is that before there wasn't a very clear definition. The definition was whatever this regex matches. Like you would have liked to say before all the type names should be blue, but we weren't able to do that before. And general purpose text editors don't really behave that way now. They say anything that like certain type names like string that I know of will be colored this way, but not all type names. Yeah.
So in your example, is the reason person is colored that way because of its position in the syntax tree and not because it's seen a previous definition of person as a type?
Exactly. Yeah. So it's doing, because types can be defined in other source files. There isn't that semantic layer that plays into the syntax highlighting. It's just syntax. It's based on like there's probably in this case there's a rule that says in a type declaration the first identifier, that's the name of the type that's being defined, should be blue-green or whatever. Yeah, as opposed to like maintaining a symbol table of all the list of known types.
So that you have a special rule that the star is going to be colored in black instead.
The star, no, I just like, right now it's expressed as like type names should be blue-green, and in Go, types can be distinguished purely based on syntax, except for actually that's not 100% true. There's one piece of syntax where you can't distinguish between function calls and type coercions. And in that case, TreeStater can't tell. It's going to color it like it's a function call as opposed to a type co-version. So yeah, it's purely based on like the syntax tree that you can build for the file, not having looked at any other source files in your project, kind of taking that syntax tree and mapping certain subtrees of it to colors. Yeah. And so yeah, there are caveats like in C, there's another problem where in certain cases you can't distinguish a variable declaration where you're declaring a pointer from a multiplication expression because they both use the star operator. So in that case, TreeSitter's goal is not to replace libclang to understand everything about the code. It's trying to like do the best it can, like a human would, to read a code and build a syntax tree for it. So in that case, TreeSitter's going to make a reasonable guess for you about what's a type and what's a variable. Good questions. So this is C, and so I was saying like basically we're able to do better syntax highlighting that's more consistent than what we had before and more specific than what we had before. And I think that once you get to this level of specificity, you really can discern the structure of this code at a glance just by squinting at it. And just to illustrate that further, I'll switch it to C. Oh, let me go back to Go. All right, here's Go. And here's the same code in C. And if you squint, you can kind of just tell that it's structured. This code has the same elements, except for now in C, the types go on the left instead of on the right. And here's the same thing in C++, and in TypeScript, in Python, and in Ruby. So in all these languages, we're able to, yeah.
So how do you teach TreeSitter about the syntax or the grammar of each of these languages? Is that just the CSS stuff that you were talking about? Where does this get defined?
Yeah, that's a separate thing. The CSS is just this like kind of, it's just the configuration for the syntax highlighting specifically, but developing the actual parser is a separate process that I'll show it a little later on and talk about how you write the grammars and how you ultimately use them, kind of after I talk about this application. So aside from these behavioral improvements to the syntax highlighting system, another way that we can do a better job with this approach is our handling of long lines in files. So if any of you have ever opened up a file with really long lines in Vim or in Atom or most text editors, you'll see this behavior where there's like a little tiny bit of syntax highlighting at the very beginning of the file, and then the rest is black and white. And so that's because the way almost all like multi-language text editors implement syntax highlighting is by performing a series of regex searches on each line of the file. And so the longer the lines get, the longer each individual regex search gets. And so the text editors need to give up at a certain point so that the syntax highlighting doesn't freeze the editor. But since TreeSitter uses like uses a regular parser and a tokenizer, it doesn't have this performance problem where the line breaks affect its performance. It can parse the file at the same speed regardless of where the line breaks are. So we're able to syntax highlight entire files even if they have really long lines. And then one final improvement is the handling of files that are just really large overall. If you've opened one of these files, a file like a megabyte source code file in almost any text editor, like Sublime or Atom or Visual Studio Code, the syntax highlighting takes a while. And some editors handle that by opening the file and letting you view it before the syntax highlighting is done. So if you were to scroll to the bottom, you'd see black and white text for a while before the syntax highlighting got to that point. On this slide, I just have an example of me parsing a 20,000 line JavaScript file in TreeSitter. And it shows that the time that it takes to parse, and it's about 69 milliseconds, which is fast enough that it's insignificant now compared to the other work that needs to happen when you open a file in a text editor. So we don't have that problem of needing to defer syntax highlighting. Yeah?
This is the speed the first time you open a file when you edit.
Right, yeah. That would be awful if it took that long every time you type. This is the initial parse of the file. Yeah, exactly. Okay, and then aside from syntax highlighting, the next thing that I chose to build using TreeSitter was a new code folding system. So you're probably familiar with code folding. It lets you hide parts of your code that you don't want to look at right now. And often text editors implement code folding using indentation. So lines that have greater indentation get hidden. And this is usually a pretty good behavior, but in some cases it kind of falls down. Like in C, it's common to write functions like this, where every parameter to the function is on its own line. And in that case, the indentation actually decreases when you get to the body of the function. So the indentation rule doesn't match your intuition about what you would like to fold. Different text editors handle this differently. I think Sublime Text just doesn't let you fold functions that are written like this. And Atom and Visual Studio Code do, but the fold comes out looking strange because part of the parameter list gets hidden inside of the fold. Well, so now by basing the decision about what text to hide on the syntax tree, we can fold this code in an intuitive way regardless of how it's formatted. So I have a little animation here where I do different things to the formatting of the file, and at every step I'm able to fold it in an intuitive way. I think at one point I even take away all the indentation from the file, and was it animating? I think the frame rate's a little too low, but okay, it's strip all the formatting of the file, and I'm still able to fold it correctly because it's based on the syntax tree, not on anything about the formatting. And this is useful because oftentimes this is a time when you want to fold something, when your code's formatting got messed up, maybe because you copied and pasted something. And so being able to fold in that scenario so you can tell if you pasted it correctly is useful. Yeah. Oh, go ahead.
Do you have an example of what happens when the code is not quite right?
Oh, is syntactically invalid?
Yeah, if I delete one of those commas, or I have to type it in or something.
That's a good, I wish I had an example. So like, what'll happen is so there's this whole error recovery algorithm in TreeSitter, and if there's a missing comma, it's going to be fine. It's going to be able to fold it okay. If there's a missing curly brace, so that the entire structure is now thrown off, that's going to affect the folding. It's going to fold, what it thinks. You know what I'm saying? It's going to change the structures that it gets folded because it's going to parse it differently because of that missing curly brace. Yeah.
I was going to ask this later, but on the heels of that question, how does, say I'm at the very beginning of my file and I delete a curly brace or something like that, I imagine that would affect considerably how parsing would proceed for the rest of the file. So does that mean that editing at the beginning of my file, like hitting the keyboard a bit, is going to mean that it's going to reparse a lot of times?
Yeah, I mean, I think you would have to do something pretty weird for it to throw off the parsing of a lot of the file, because even if say you have a class definition with a bunch of methods inside of it and you deleted the top of the class definition so it's no longer a class, still a lot of pieces of that tree can be reused wholesale. Like the entire bodies of functions are still they're still statement blocks, and those don't need to be parsed. And so it shouldn't cause too much of a performance problem, even for editing patterns like that. I think one thing that might is if you had your entire file commented out via a block comment, and then you deleted the delimiter of the block comment, so now it's all code, and then you went back and forth. That would be a little bit slow right now. That's something I have to work out, is when the parser should kick into a background thread to parse, because it's too big of a change just happened. Right now, you might just observe a little bit of lag when you uncommented your entire file, that type of thing. Although commenting it should be fast. So anyway, yeah, that is harder than it would be with a dumber syntax highlighting system, because those types of localized changes can't have such a big ripple effect usually when you're just matching regexes on the file line by line. Yeah.
All right, I can't hold it back anymore. I feel like I really like your basic premise, which is that really we're manipulating code. So why should you use all the weird text kind of manipulation techniques, right? You're like, oh, reg expressions, those aren't really respecting the semantics of what you're really doing. I mean, not semantics in terms of programming language semantics, but semantics in terms of what you're representing, which is this code block, and all of these examples are just, oh, you shouldn't try to do syntax highlighting basic on regular expressions, right? That doesn't really whoa, that's going nuts.
Oh no. Huh.
Anyway, my question is like, so why can't the storage also work that, right? Well, they would work that way, but the storage on disk of your code, right? And the representation in memory of your code, like why do we need text-based, editors at all, right? I mean, geez, I mean, all these things would be solved, right? You just didn't have to parse things as you go, right?
We just made a standard for everything.
If,
That everybody agreed on.
a scan, well, what do you mean
A standard for representation of program that everyone agreed on.
if you just had, I mean, there's a tree-based structure, right? You can just delimit it with open and closed parentheses all the time. It wouldn't even matter, right? Okay. I mean, like, there's people are very wed to exactly what they typed in. And people, programmers have, like, been doing this since they learned to program, and sometimes that's been a long time. And they want to, feel like they control something, or I don't know what it is, but, like, why do we need
Why
text?
didn't you change all the programming languages?
No. I mean, I understand. I want to, like, we're talking about future looking, right? I mean, like, how are we going to solve this problem, right? I mean, is this the right thing in the future? Is this for the next 5 or 10 years to get people to, like, understand stop writing your compilers and your syntax highlighters in the stupid way and use some, modern technology? Are we going to change the world and get people to stop using text editors? Are you going to let me rant this whole time? Anyway.
I'm not going to stop you. Yeah.
Okay. Fair enough.
Yeah, I don't know. I mean, I definitely believe in that idea too of structural editing being like more efficient. But this next thing I'll show you is like I'm kind of really dipping my toe in those waters that you're talking about with this tool, and I haven't thought too hard about like changing all our compilers and stuff. One thing I do feel though is like text is pretty easy to manipulate, and it's going to be hard to supplant the ease and fluidness of typing to me. And parsing is pretty cheap, so for me, like there isn't. I feel like a lot of room for improvement exists in this this box that we're in right now, whether it's like a mental box or not. But anyway, yeah, I totally agree. Like, what was it? So like here's this. Let me just show you this other command that I built. I don't know. It's not a revolution like that, but
Oh, I'm sorry.
Oh yeah, I realized. So I apologize for not repeating the questions too. That just occurred to me as I tried. Was like, how can I repeat his question? Okay. So I added this command to Atom called extend selection, and it is kind of a tool for structural editing, like in the direction that you were talking about. But all it does is you tap this command and it selects larger and larger pieces of the syntax tree so that you can quickly grab some kind of code that you want to edit without having to carefully move your cursor around. And what's really cool is when you use extend selection with multiple cursors, you can do these really fast transformations. Like in this example, I'm reformatting this whole data structure using a combination of extend selection and multiple cursors in this way that would actually be very time consuming to do if you didn't have this tool. This is a command that existed in IntelliJ editors that I always was really inspiring to me because it makes the experience of editing feel like you're editing this structure, not like you're editing lines and characters of text. So it feels really good to me. It's I think it's like and it's something you just couldn't build if you didn't have a syntax tree available in the editor at all times, obviously, because the whole point of this is to select nodes in the syntax tree. And so I think you could do more things like this to make it feel more like you're dragging and dropping pieces of syntax as you edit, rather than always working with characters and line breaks, things like that. And then the final thing that I'll show you that I've done so far in Atom, whoops, skipped it, is that when you move your cursor around and you land on a local variable, I can now highlight all the places where that local variable is used and underline the place where the local variable is introduced. This is a pretty familiar feature, I think. That other text editors do this in different ways. Well, I think Visual Studio Code does this for a select list of languages by calling out to an external language server that provides code analysis and tells the editor what ranges to highlight. But what I like about the way that I did this is that I just kind of hacked this in a couple hundred lines of JavaScript that, when you move your cursor, it inspects the syntax tree and applies the scoping rules of JavaScript to find the instances of your local variable. And it was really easy, and it feels very familiar if you've ever used JavaScript on a web page to manipulate the document. You traverse through the tree and make changes by looking for certain nodes. It feels very much like that, and so I feel like, in Atom, the whole point of it is to be this hackable text editor, and people already do these amazing things to kind of code intelligence features just using regexes and things like that. And so I think giving them this syntax tree that gives them this whole nother level of accuracy in terms of analyzing their source code will really improve Atom's hackability and allow package authors of Atom to do more creative, cool things to your code while in Atom. So just recapping, what I've done in Atom so far: better syntax highlighting system, better code folding system, this new structural editing command, extend selection, and this local variable highlighting feature that I hacked in, and so hopefully will be indicative of what other package authors can do given this syntax tree. So aside from Atom, we're also using TreeSitter on GitHub.com now. We recently released this feature where when you're looking at a pull request and you open up the list of changed files on the pull request, you can now see within each file a list of the functions that have changed in the file in the pull request. So this gives you this nice summary of what somebody did in their pull request and lets you navigate the pull request according to these meaningful units of functions. This was built by a team in GitHub's data science division that I think some of you may know some people on that team. It's managed by Rob Ricks, who's a fellow Haskeller, and they use Haskell. And so they've digested a lot of research about source code analysis and are using a lot of cool algorithms for analyzing syntax trees and comparing syntax trees to each other. And they do all of their parsing using TreeSitter because it gives them this uniform way of parsing many different programming languages. And so between the work that they're doing, that team, on GitHub.com, and the work that I'm doing in Atom, we're developing this shared set of parsers that work for more and more different programming languages together. And I think that once I actually ship all these Atom features that I showed you, which are still kind of in alpha right now, then I think this set of parsers that exist will grow even faster because now all of this huge community of Atom users will be able to contribute support for more and more different languages. And so we'll all be able to use this shared set of parsers so that in the future, when you want to do this kind of analysis in any programming tool, whether it's us on GitHub or in Atom, but any tool that you use that supports many languages, you'll be able to use this one C library, TreeSitter, to parse any language that you want. And this team that's built this is got a lot of cool things in the pipeline. They've showed me things where you can, I don't know if you're familiar with the GitHub.com GraphQL API. It's this new API for accessing data on GitHub where you use this language GraphQL that lets you specify kind of exactly what data you want in this nested way, and then you get back just that data. And you can even, they'll extend that to include the syntax trees. So in the future, you'll be able to say, I want all of the users who contribute to this and look at their pull requests and look at the functions that they changed in their pull request and see if they introduced any new function, like calls to malloc or something crazy like that, using the GraphQL API. So I'm really excited about what people will do with that type of power. Okay, so that's what we've done so far with TreeSitter. Now I'll talk about how it works. And so first I'll explain in more detail what it looks like to use the library, how you use it, how you add support for a language. So when you want to add support for a new language with TreeSitter, you need to write what's called a grammar for the language. It's pretty familiar if you've worked with parser generators before. The grammar lists all the elements of the language and specifies how they can be built up out of other elements of the language. And one difference with TreeSitter from other popular parser generator tools like Yak and Bison is that rather than writing your grammar in some special grammar definition language, you just write your grammar in JavaScript, and the grammar is represented as this simple JavaScript object that you can build up using a few simple JavaScript functions. So it feels kind of like if you've ever used a parser combinator library like parsec in Haskell, it feels a little bit like that, where you can move your code around at will and extract different named helper functions, that type of thing. Although under the hood, it doesn't work at all like parsec. It's a lot more like Yak and Bison. It's a generator of a parser. But so let's see. Once you've written your grammar, one more thing about the JavaScript object representation. The reason that I did it that way, as opposed to using my own version of, BNF notation or something like that, is that not only do I like the experience of the parser combinator style, but also it lets you can, it's really useful to be able to define a grammar by loading another grammar and then modifying it in some way and then re-exporting that as a different grammar. Like I use that technique to define the C++ grammar in terms of the C grammar and define the TypeScript grammar in terms of the JavaScript grammar. Okay, so once you've written your grammar,
Yeah, that's a question. So to support the incremental parsing that you mentioned, does that require any special support in the grammar? Does the grammar have to take that into account anyway, or is?
No, not really. Like the grammar itself just needs to be, really any context-free grammar is supported, although the closer you get to an LR grammar, which is this like class of context-free grammars, the better performance you will get. And so anytime you diverge from LR, like the system requires you to explicitly acknowledge that you're opting out of LR for a certain scenario. So you have to there's this list of conflicts that it's a whitelist. You say, I only want to allow certain conflicts because the system tries to push you toward writing an LR grammar. But that's not a very tight restriction. LR is a really large class of grammars. Yeah.
Yeah. Is there any class of languages that it just won't handle?
Not that I know of. I think the hardest things are, the paradigm is model your language as using a context-free grammar, which is just, this can be built out of that. This can be built out of that. It's a pretty loose. It's not a very tight restriction, but it is can be challenging for languages that have like a pre-processing nature to them, like where there's sort of one language that's processed, and then once that's all done, another layer of processing happens, like with PHP, where you process the PHP and then it outputs HTML, and so we'd like to then parse that HTML as well, at least in some way. So that's the most challenging thing, languages like that. We've done some of that. We have a PHP grammar, but right now it doesn't parse the intermediate pieces of HTML in between the PHP tags. That's going to be the hardest thing. We're going to have to, of course, approximate it. It's same thing with the C preprocessor, where there's just there's no way we're going to be able to replicate 100% the behavior of the C preprocessor. So what we have to do is model it as if it were part of one coherent language. Include in the language the various patterns that you do with the C preprocessor, like including files and defining macros, using macros. And so, that's an important thing about TreeSitter is it's doing the paradigm is do the best you can to understand a language using a context-free grammar. You're not going to be able to write a compiler based on that. You're not going to be able to rewrite Clang based on that, but it's going to do a whole lot better of a job than running regexes on the file or the typical things we might do. Yeah.
So when you write this grammar, typically a tool like Yak or something might tell you your grammar is actually ambiguous, like there's no use count. Is it?
Exactly. Yeah.
You know about stuff like that?
Same thing. Yeah. If your grammar has an ambiguity or even a local ambiguity, that's where it diverges from our subset. And you run TreeSitter on it, it'll give you an error that says ambiguity. Here's the sequence of tokens that had to happen in order to reach this ambiguity. here's the 2 different trees that I could potentially build using this sequence of tokens. And at that point, you can either, most often what you want to do then is restructure your grammar a little bit so that it doesn't have that ambiguity. But then sometimes you just want to like do it anyway. And so that treesitter has a mechanism for opting into specific conflicts where you can say, like it comes up in C, in that one diabolical scenario I mentioned earlier where you can't distinguish a pointer declaration from a multiplication, it'll say like basically you have to write something in your grammar that says something like that lists the things that are in conflict with each other. Yeah, like type and expression, that type of thing. So anyway, yeah.
I was just wondering, is there any special built-in support for writing grammars for language with their layout sensitive?
Yeah, it's not built in, but so we have a Python grammar that is, I think, as far as I know, like one tested really thoroughly. And the way that the hook that I give you to do that is it's in the lexer side of things. It works similarly to the way these languages work in their compiler. Is the lexer has some custom hand-coded C logic that produces these special tokens, indent and dedent in the case of Python. And so treesitter has a mechanism where, like, for the most part, it generates the lexer for you. You don't think about the like parser-lexer distinction explicitly necessarily when you develop the grammar. You just, like, I'll go back to the screenshot of the grammar. You just kind of include the text of the tokens in the grammar itself, and it's this unified representation, and then it figures out how to produce the lexer. But in scenarios like that, there's a hook for what's called an external scanner. Like you can write your own custom C code that its only job is to produce indent and dedent tokens, and it's Python to carry this stack of like indent lengths that that capture your state. Yeah. Next question.
So I guess first question is, does this work with Haskell?
Yeah. So I have a plan so Haskell's layout rules are a little more complicated than Python's, as I'm sure you know, because it matters not just the indentation of each line, but where the word if appeared on the line, because the indentation is based on the location of the actual keyword if or lambda or whatever. It'll work, but I'm going to need to add a way. The only wrinkle to it is that in order to support incremental parsing, any feature that I add, any like expressive power that I add to the scanner needs to keep in mind the fact that it's going to need to be able to update the syntax tree efficiently. And so in Haskell, what you want is in your external scanner, when you encounter a special keyword like lambda or if that starts that has the potential to start an indented block, I think you need to be able to ask what column you're at that time to say like, all right, I see the word if, what column did it start at? And that's the column that I need to store in my indent stack. Unlike in Python, correct me if I'm way wrong here, by the way.
No, that's good, but there's also, I think it's kind of moot, but I was curious because there are things that you can say in the header of your source code which can affect the indentation-based parsing that goes on.
Oh yeah, so I don't know what that is. Maybe we could talk after. I know there's things in Haskell that are like not context-free, like declaring the fixities of your operators. That's not going to work. We're going to have to do the best job we can to guess what the precedences of operators are and things like that. But yeah, I wasn't aware that the actual indent rules themselves can be influenced by the code. Yeah.
I was curious, Lexer usually does comments as well. Where does that go?
Yeah, there's a special construct in the grammar that I added to context-free grammars that's just called extras. And that's where you declare things that can appear anywhere, and they're handled by the lexer. So you declare that comments are a form of extra, and that means that your lexer will, no matter what state your parser is in, it'll always look for comments and consume them.
Comments are tricky when you have a syntax tree that you kind of want them in the syntax tree, but they can kind of be anywhere, so match their real thing. So presumably, usually compilers just throw them away. obviously here you don't want to throw them away. So does the syntax tree kind of keep comments in any possible position?
Yeah, it can. And so I've gotten some feedback from the data science team that is using this for more analysis type tasks, that comments are tricky for them because, yeah, the way that I model them is they just appear in the tree wherever they occur. And so because I haven't really talked about the tree API, but it's a very simple, like, I modeled your program as basically like an S expression. It's just an ordered tree. It's not, children don't have names associated with them. They're just children. And so the presence of comments in there makes it a little more challenging to identify what, when you're looking for a certain child, the fact that a comment could be in there affecting the positioning of the other children is complex. So right now the comments are just in there. They're marked as extra. So you can do any analysis you want, and you would have to just account for the fact that comments are going to be there. And that's what I do right now. You just kind of have to deal with it. Yeah.
So I'm kind of interested in failure recovery. So if one of these, like as you're typing in an editor, usually you don't have a fully formed program at any given moment that you're typing. Usually it's halfway done.
Yeah.
So how does the grammar, like how do you handle failure in a nice fashion?
I have some slides about that, so maybe I'll just.
Okay, sounds good. I'll wait till then.
Yeah, good question though.
So I want to ask really quick.
Yeah.
So once you've got this parser, right, and it does all this like sweet incremental parsing going on, and you want to like say you want to write something to use it, right? Say you, for instance, hate the way other people invent their code, and you want to have it edited for somebody, right? I mean, is it pretty simple, and you have a nice API for just interacting with parse trees? Is that kind of the idea?
Yeah, I have a slide about that too. Let me advance to that.
Okay.
Well, so I guess we already kind of talked about this, but the thing that gets generated by this process is this one C file that has two parts to it, the lexer function and the parse table. And I'll just gloss over that. But yeah, when you want to use the parser, there's a simple C library called the treesitter runtime that you use to actually run these parsers, so that it exposes a simple object model where you make a document and you set the language on the document. The language is the struct that's exported by this generated file. And then you can parse code, and you can access now the root node of your document, and then you can use this tree API on it, kind of a minimalistic API. It's just a tree of nodes where every node has a type and has it knows where it starts and ends in the document, both in terms of raw bytes and in terms of rows and columns. And it has an ordered list of children. That's it. And so this is the C API, but usually you would use it through some higher level language. Like in Atom, we have JavaScript bindings to the C code, so we can write JavaScript that walks the syntax tree and does the kind of thing you're talking about, potentially edits the code based on the syntax tree. And there's also Haskell bindings to this code right now that the other team that uses this at GitHub has developed. So yeah, that's what it looks like to use the library. Now I'll talk about some of the algorithms that treesitter uses. So they're mostly based on this research that was done in the 90s at UC Berkeley, and in particular this PhD thesis called Practical Algorithms for Incremental Software Development Environments by this guy, Tim Wagner, which is a huge treatise on everything pretty much that you need to know to do parsing in an IDE. So it talks about which of the basic parsing theories you should rely on, and then how to augment that theory so that it can handle incremental updates. And then it does these proofs that the incremental updates have good performance characteristics. It talks about how to handle errors and ambiguities in your language, and a bunch of cool ideas in parsing. And so the basic, as I said, the basic parsing framework that it relies on is LR parsing. And many of you are probably familiar with LR parsing if you took a compilers class in college. I didn't do a computer science degree, so in order to build this, I had to go learn about LR parsing on Wikipedia, which was really great. I really recommend the Wikipedia article about it. But I thought, even though it's a pretty generic idea, LR parsing. I'm going to just go over it really quick because I'll build on certain aspects of it in order to talk about the more unique parts of TreeSitter. So as with any type of parsing, the goal is to convert this sequence of characters that has this implicit structure to it into a tree that explicitly describes all the structure. And the way that an LR parser does that is it reads the characters from beginning to end without ever backtracking. And as it goes, it groups them together into tokens using the tokenizer function that TreeSitter generates. And it groups those tokens into subtrees that it stores on a stack. And at every step, it decides what to do with its stack by consulting the parse table based on its current state that the parser's in and the next token that it sees. And so when parsing a simple math expression like this, it would start at the beginning of the code with an empty stack and in some starting state, call it state 0. And it would run the tokenizer function, find out that the first token is a variable x, and look at the parse table to see what to do with that variable, and it would find a shift action, which means that the parser should push that token onto its stack. And the same thing for the next two tokens. Then when it gets to the plus token, it sees the other type of action in the parse table called a reduction, and that means that it needs to hop off of its stack, these three nodes, and group them into a new parent node called a product and push that back onto the stack in their place. And then so on, and the same thing for the sum node. So that's the basic idea. And so like a question that you actually already asked and is a good question is like, does this one theory of parsing, LR parsing, work for all the programming languages you could possibly want to model? And the answer is no. And I wanted to show you one of the quirks that programming languages have that cannot be handled by LR parsing. So these are two pieces of JavaScript code. The first one, we're assigning to the variable x the value of the variable y, which we have wrapped in parentheses for no reason, but just because we can. And then in the second example, we're assigning to x this arrow function that takes a parameter called y and returns z. And so the thing about these two pieces of code is that they look the same all the way up through the right parenthesis, but the syntax trees that we would want to generate for them look different even for that beginning part of the code. So in the first example, y is an expression. It's a variable that we are evaluating. And so the syntax node that represents y needs to be wrapped in an expression node, which is the type of node that represents the fact that we're evaluating something in JavaScript. And then in the other example, y is not an expression. It's just the name of a formal parameter, so it has this different structure to it. So let me show you how TreeSitter handles that. Well, I don't know, is that clear why that's, yeah, okay, nodding. I'm going to skip over some stuff that I might otherwise say. So the way that TreeSitter handles that is with this theory called GLR parsing, which just stands for generalized LR, and it's the enhancement to LR parsing that lets us parse literally any language that you can write as a context-free grammar. And to show how it works, I'll just walk through the example of parsing this second piece of code, the arrow function. And so what's on this slide is a series of diagrams of the parser's stack that are kind of like the stacks that I just showed a moment ago. But these are diagrams that are generated by TreeSitter itself. You can run the parser in this mode where it outputs these graphs at every step to help you debug what the parser is doing. And so what's over the lines in the stack are the names of the trees, and then what's in the bubble is the state number that the parser is in. So you can see that the first four steps are familiar. All the parser is doing is pushing tokens onto its stack. But when it gets to the right parenthesis, that's where it needs to decide whether the y should be interpreted as an expression or not. And so what GLR parsing does is it simply splits the parse stack into two branches so it can simultaneously explore both interpretations, but still never backtrack because it can kind of keep them all up to date as it advances through the code. And so on the top branch, you can see that there's the y, oops, touch screen. The y is just represented as an identifier, and then on the bottom branch, it's represented as an expression. So the top branch is the one that we're ultimately going to want. And then you can see that it continues parsing with both branches for a few steps, but then when it gets to the arrow token, well, that wouldn't be valid after a parenthesized expression. So at that point, we can chop off one of the branches of the stack and then continue parsing using normal LR parsing. So the great thing about this is that, as I said, it lets us handle any context-free grammar. And in practice, most of these kinds of local ambiguities in languages are fairly localized. They'll occur in the span of a few tokens. And so it doesn't really, unless you go crazy with these constructs, it doesn't really affect the performance of your parser at all. And then you can see that it continues on to the rest of the code in a linear fashion through normal LR parsing. Okay, so yeah, question.
So real briefly, before you get into error recovery, if you're at a certain point in the code and all that type is x equals parenthesis y parenthesis, now your GLR has two possible results for that. So how do you decide in tree parsing which one?
Oh, you mean if that was all there was in the code is just x equal in parentheses y? Well, then there would only be one valid interpretation, the former interpretation, where y is an expression in parentheses, because the second interpretation requires there to be an arrow after the parentheses. Does that make sense? So like for any given, I don't think that this construct of parenthesized expressions versus arrow functions ever introduces any actual ambiguities in JavaScript code. They're just these local ambiguities where while you're in the process of parsing it, you can't tell which one is going to emerge. But by the time you're finished, you can always tell which one.
So
right.
In the application in Atom, if I've only typed this fragment of code, I might get an incorrect highlighting, for example, because I will be looking at one possible parse tree versus the other.
So if you're in the process of typing an arrow function, but you haven't typed the arrow yet, then yeah, Atom's going to parse your code as not an arrow function, just a parenthesized expression, which is what it should do. But yeah, so the highlighting might change as you type, which is I think expected. Yeah, so like that approach is what is the main thing that allows TreeSitter to be so general as to parse many different programming languages, is that we can avoid the kind of, in the actual, for example, the V8 JavaScript runtime, it has a JavaScript parser that does all kinds of ad hoc code for handling arrow functions and backtracking, and there's just a bunch of custom logic that we can avoid in TreeSitter by using GLR. So that's what makes it easy to model lots of different languages. How are we doing on time, by the way? Like, is it okay that I still have like a lot of?
We are at the end of time. We should probably try to wrap.
Okay. All right. Well, so error recovery is something that you asked about. So most parsers, when they get to a syntax error, halt and give you an error message, and that's it. Their job is done. But TreeSitter needs to keep on parsing the entire rest of the file and do the best it can to give you back a syntax tree where the tree itself encodes where the errors are. And so here's an example where you have a JavaScript if statement, and then somebody started typing a for loop before the if statement. And so the code looks like this. And here's the syntax tree that TreeSitter would want to generate, where it parses the if statement in its entirety, but the tree just contains this one special type of node called an error that just indicates the fact that the word for is not supposed to be there. And similarly, you might have actually a full-on for loop where you just type the word if accidentally. And in that case, too, TreeSitter would parse the whole for statement, but have an error node that represents the fact that the word if is not supposed to be there. Yeah.
So to summarize, this is GLR parsing, except every time I need something that's completely unexpected, I push it on as an error token.
It's a little more subtle than that, it does leverage the GLR algorithm in order to do this, because so the hard thing about error recovery is that just with plain LR parsing, you can identify the presence of a syntax error as soon as mathematically possible using this algorithm, but you don't know what the error is, what nodes are incorrect and which ones are correct, and identifying that is kind of a fuzzy thing that requires heuristics. And so TreeSitter's heuristic is it's going to try to remove certain node tokens from the program and remove as few as possible in order to produce a good syntax tree. But even that is really not trivial, because as you can see here from these two examples, they start out the same, but the correct recovery is different in the two of them because of the difference in the later pieces of the code. And so TreeSitter uses the GLR algorithm to resolve that problem, where it kind of, when it gets to a syntax error, it splits the parse stack into two or more branches that each try a different way of recovering from the error. So here, there will be one branch that skips the word if, and then one branch that actually pops off the word for and tries skipping that. And they'll both proceed for a while until one becomes clearly better than another. And so in the first example, after a few tokens, it'll decide, okay, I need to skip the word for here because I've got an if statement that follows. And then in the other example, it ends up skipping the word if because what follows is actually only makes sense as part of a for loop. This is kind of the hardest part of TreeSitter because it's not, you have to use heuristics in order to do this properly. Yeah. What was that?
Does it ever insert missing things like semicolons?
Yeah, I want to add insert. I think what I'll do, I don't want to take it too far because there's already so many options to explore, and that it's a little bit of a challenge to make it perform well. But what I think I will do is add a feature where it'll try inserting one token, and that'll capture a lot of common cases like leaving off a semicolon, leaving off the conditional in your if statement inside the parentheses, things like that. So yeah, you could. I haven't done it yet though. Right now, it's all about just skipping the least amount of trees possible. And then the final thing I wanted to show you is the way that the incremental parsing algorithm works. So here's an example where there's 3 JavaScript statements, and then you edit the second statement, you insert an argument to this function call. And so the way TreeSitter processes that information is that when you do the edit, it looks in its existing syntax tree and finds all the nodes that contain the place where you edited, and it marks them as, in this case, having had a character inserted into them. And then when you go to parse, it actually proceeds to do parsing using the normal algorithm as if it were going to parse the entire file from scratch. But now, as it proceeds with its parsing, it has the old syntax tree as a reference. And so it can reuse parts of the old syntax tree. So when we're at the beginning here, TreeSitter can kind of look in the old syntax tree and find the first node that's at this same position that has not been edited and that is compatible with our current state. And it can just push that directly onto its stack. So in this case, it pushes the whole variable declaration onto its stack. And then similarly, the statement has been edited, but there's part of the statement that hasn't been edited, namely the member expression at the start of it. So it can reuse that in its entirety. And it can even reuse the left parenthesis that immediately precedes the edit. And then when you reach the actual site of the edit, then you have to parse from scratch using the tokenizer and everything as normal. So it uses the tokenizer to build a new identifier token. But then it can again reuse old pieces of the syntax tree